Okay, going back to section 3.2, implicit differentiation, class notes, part 2, we want to revisit this as a second day. A function is said to be explicit in explicit form if it's in the form y is equal to f of x, and a function is said to be in implicit form if it is not solved for y. For example, the function xy is equal to 1 is in implicit form, but the function y is equal to 1 over x is explicit form. So with this, we'll start off and we'll say that we are able to analyze curves that define y implicitly as a function of x. So we need a method since some can be solved for y and some cannot. The general rule is to remember that y is a function and the derivative of y is then dy dx. So if you recall, we did a few warm-ups with that idea in mind. So keep in mind that when you take the derivative implicitly of the equation y is equal to x squared, and I'm going to just put some brackets here, x squared plus x, you're taking the derivative of x on the right-hand side, but on the left-hand side, you're taking the derivative of y. So you're going to get dy dx on the left-hand side, but on the right-hand side, taking the derivative with respect to x, what you could do is you could say this. You could say, well, it's 2x times dx dx, which is kind of equal to 1 anyway, plus 1 times dx dx, using the chain rule. So you're taking the derivative with respect of x with respect to x, so it just is going to be the derivative, which we get then dy dx is equal to 2x plus 1. So using the chain rule, there is no inside function, so to speak. It's the derivative with respect to x. So being x then, there it is, there you have it. So on the next one, we have the derivative with respect to x of just x, and then on the right-hand side, we have the derivative with respect to x of y cubed plus 2y. So on the left-hand side, the derivative with respect to x of just x is just going to be 1. And on the right-hand side, we've got 3y squared, and then I'm going to multiply by the dy dx using the chain rule there. 3y squared, taking the derivative of the outer, y cubed, and then the derivative of the inner, where y is a function of x. So we're going to have to take the derivative of the inside. That's our dy dx, plus then we have 2 times dy dx there. Now, the nice thing, if you have all y's on one side of the equation, you can wait till the end and it would just be like at this step, you're going to say 3y squared plus 2, and then you're going to factor out a dy dx. So you might say to yourself, well, why can't you just wait till the end? And that's absolutely true, that if you only have y's on that side of the equation, you can easily do that. And then just tack on the dy dx at the end. So now let's isolate the dy dx. So we get dy dx is equal to 1 divided by 3y squared plus 2. And it is all right to have a derivative in terms of y instead of x. It just happens that our derivative is dependent on y rather than being dependent on x. Okay, so there's that one. Okay, now the rules for implicit differentiation are you differentiate both sides of the equation with respect to x or whatever variable you're told to, and then collect all the dy dx's to one side, all the terms that have dy dx in them, and then solve for dy dx. So it kind of reminds you, I think I had mentioned this before, is if you have that situation in algebra where you have ax plus bx is equal to c, and it says solve for x in an algebra 1 class where you would say a plus b times x is equal to c. You would factor out the x, and then you would say x dividing both sides by a plus b. You would get that kind of a situation. You're going to do that here. So you look at the next problem, you say, okay, well, what is this first? X squared plus y squared is equal to 34. It's a circle with the radius, a circle centered at the origin with radius square root of 34. Okay, and then you want to find the slope after you get the dy dx, and then at the particular point, 5, negative 3. So just very quickly, if we're looking at a circle, since it is centered at the origin, we can actually do this pretty easily. And you know that the radius then has to be 1, 2, 3, 4, 5, 6. So a little shy of that. It does not have to be perfect by any way, shape, or means, but let me just go up and go down. And let's see if I can draw a pretty good circle and fit it in there, or like somewhere around there, right? So if we can just estimate, if we have the point 5, negative 3, wouldn't it be somewhere, 5, negative 3 would be somewhere about right here, right? right here. And so we would look at that 5, negative 3, right? And there's the point. So we would say, well, it definitely has to have a positive. Here's the tangent line there, right? And there. So it would have a positive slope to it. So here we go. So we're going to take the derivative with respect to x of the left-hand side. X squared plus y squared is then equal to the derivative of the right-hand side. Derivative with respect to x of 34. And on the left-hand side, we're going to get 2x. And it's x, so we don't have to put anything with that. But then we have a 2y, and then we'll have to tack on a dy dx using the chain rule. Okay, and the right-hand side, we get 0. So now we have 2y dy dx is equal to negative 2x. And then we're just going to multiply both sides by 1 over 2y. I guess you could say it like that, 1 over 2y. So then we could simplify that. And I apologize for the red here. Try not to use that color. 2x over 2y, and so we get dy dx is then equal to negative x over y. So there is our derivative, and box that up for a second. It's going to be used, and then what am I doing here? Boom. Okay, so now then I want to find the slope of the curve at that 5. Move all this over here. So then we want to find the slope of the curve at that point. So we have dy dx. Here's language we very often use when we do a vertical line like that. We'll say evaluate it at the point. Sometimes we'll go like this, evaluate it at 5, negative 3, and put the ordered pair there. And since it's negative, then the x value is 5. So negative x over y. So that's going to be over negative 3. So we get a slope of positive 5/3, and that checks out. And since we want the slope of the curve at that point, if we wanted to do the equation of the line, that would be fairly easy, but it makes sense that the slope is then 5/3. Okay, now if I had to, I could say, oh, that line then would be y minus a negative 3, which would be y plus 3 is equal to 5/3 times the quantity x minus 5. And there we could easily have the equation. We didn't ask for that. That's an extra one, but I won't charge you for it. All right, so I'm going to do one more on this video, and then I'll have to hop off and get a second video going. So now here we have dy dx we want to find, but we have an x squared times y and a sine y. So you have to be careful that you think before you go ahead and start doing derivatives, because with these two, x squared y, we're going to have to use the product rule. And then we have a sine y as a trig function, and then 10, the derivative of that side is just going to be 0. So here we go. We're going to take the derivative of the left, and I'm going to be very thorough with this, where I have x squared y plus a sine y. I'm going to take the derivative of the left, and that's equal to the derivative of the right. Now remember that this is not the derivative. When I say d dx, that means you're going to take the derivative. So we have the product rule, remember, first or second. So we have first, and then we're going to take the derivative of the second, which is dy dx. Now, I probably should stop, and I often think about this because actually when you're teaching, a good thing to do is to say, all right, we'll keep the first, and then we'll take the derivative of the second plus the second times the derivative of the first. So I'm going to be a little more deliberate with this. And then, okay, that's the whole product rule. So this is the one I just did. Okay, so that's the whole enchilada for that. Now let's move on. So we have the plus sign. The derivative of sine y is cosine y, but then we have to use the chain rule with the y, and that's times dy dx. So now I've taken the derivative of, let me see, I use a dark green here. So the derivative of this one then is right here. Okay, sorry about the green, a little sloppy, but okay, is equal to the derivative of 10 is just going to be 0. So now I'm going to get all the dy dx terms together, but I'm not really quite ready yet. So I've got to finish this product rule here, right? So let me go like this. Oops. And so then I end up with x squared dy dx plus I've got y times the derivative of x squared. So I'm going to just make that 2x. I'm going to put that in front, 2x and then times y. There's no dy dx on this term. And then I have plus cosine y dy dx is equal to 0. So I think we have everything there. Now I'm going to keep all the dy dx terms on the left-hand side of the equation. So I'm going to leave the x squared dy dx plus cosine y dy dx, and I'm going to pull out the dy dx factor from both of those. And then I'm going to subtract the 2xy from both sides. So the equal sign, of course, you can see is right here, has now moved to here. Okay, we want to isolate that, so we're going to divide both sides then by x squared plus cosine y, and I think we're almost home there. And we end up then with dy dx is equal to negative 2xy, and then that is over x squared plus cosine y. Okay, and there you have it. There it is. There you go. Now, the interesting thing is I like to take the original equations sometimes just to see what they look like and put them in a Desmos or something where you can graph relations like that, and then also graph the derivative itself and see what they look like and make some sense out of it, especially when we have graphs that we're really not familiar with, even ellipses or hyperbolas, things like that. Okay, so I'm going to stop right there. So again, we worked on implicit differentiation, got a few examples out there, and I'm going to make these 2 videos instead of 1. It's a little easier to save them. And this is 3-2. It'll be the part 2 videos. Part 2 or part 1? Now I forgot. It's part 2, right? So, and I'll pick up with the second video on 3-2 part 2. All right.